Hello scholars, welcome to Comparing Two Means Confidence Intervals. Here's a little Garfield comic strip to get you going. Taking a look at tomorrow's weather, the high temperature will be between 40 below zero and 200 above. This guy's never wrong. So the question is, what is the weather reporter's confidence level? And would that be a useful confidence interval? Think about it. Okay, so the conditions for inference are the same as they have been. You have two samples and you're looking for the difference, mu1 minus mu2. You have to check for randomness of both groups, independence, which can either be that each group has no effect on the other, or that it's sampling with replacement, or you can satisfy the 10% rule for both distributions, which is n1 greater than or equal to 10 n sub 1 and n2 greater than or equal to 10 n sub 2. For normal, you can see first if it tells you if the population distribution is normal. If not, you can try to invoke the central limit theorem by seeing if your sample sizes are both greater than or equal to 30. If that's not working, then you can graph the distribution if the data is given to you. If not, you just need to continue. If any of these checks don't work, just make a statement about them not working and continue. So the degrees of freedom formula is very, very scary for this, but the good news is we have another option that we're going to use. So you have seen this formula. You might recognize it if you see it, but you don't need to use it because we have this other option, option 2. Now this option is a more conservative option, so therefore our confidence interval will be a little bigger than we necessarily want. But you're going to basically just choose the smaller sample size of the 2 and subtract 1. So this option is more conservative and gives a larger margin of error, which means it's a little bit less of a pinpointed confidence interval, but that's okay. We'll just be more conservative. Okay, so here's your formula for confidence intervals for two sample means, or two population means. T star is your critical value using the appropriate degrees of freedom. So you might want to screenshot this so you have the formula handy. Okay, here's a problem that we're going to do in our template. So you can grab the two sample template from off a canvas and do this problem together. So a safety inspector is brought into a large assembly plant to do a study to determine the difference in the numbers of accidents per month occurring in two departments. A random sample of 10 months is done for Department A, and a different random sample of 12 months is done for Department B. The mean number of accidents in those months for Department A is 12.3 with a standard deviation of 3.5. The mean number of accidents in the sampled months for Department B is 7.6 accidents with a standard deviation of 3.4. And the population of the number of accidents in each department can be assumed normal. So we're going to perform a 90% confidence interval to determine the difference of average accidents per month for the two departments. Okay, so sometimes it's easier to start with your sample sizes. So my sample size for Department A is 10, and my sample size for Department B is 12. And X bar 1 is 12.3, and X bar 2 is 7.6. With a standard deviation for Department A of 3.5 and a standard deviation of Department B for 3.4. So going back and thinking about what is our population mean that we're looking at the average number of accidents in Department A per month. And then the same thing with department B for mu sub 2. So we don't actually know the number of accidents for each of those, but this would be the population total number of accidents in department A and the total number of accidents in department B. So given to us in the problem, our confidence level is 90%. And the degrees of freedom, according to the more conservative option, I take the smaller sample size, which is 10, and subtract 1. So my degrees of freedom is going to be 9. This is a 2-sample t interval for the difference of means. And we want to perform a 90% confidence interval for the difference of means in number of accidents in Department A and Department B per month. Okay, so just a review on how we find T. So we need our degrees of freedom and we need our confidence interval. So if we're looking here and we look down at the bottom, so 90% is what we're looking for our confidence level, and our degrees of freedom are 9. So we're going to follow that over to 90%, and we get 1.833. 1.833. So going back up here, our T star is going to be 1.833. Alrighty then. So I've already done the checks for you, so you can go ahead and screenshot these checks. These were actually some pretty simple checks. So the random samples, the population distribution is assumed normal in the problem, so the sample distributions are also normal. And you don't have to use the formula for this one because the number of accidents in Department A have no effect on the number of accidents in Department B, so they're definitely independent from each other. If you did use the formula, it'd be kind of difficult because you don't know the number of accidents total in each department, but you could also use the formula and just make a statement about that. Okay, so now we're going to actually do the do. So we're going to use our formula for the confidence interval. So I need to use x bar 1 minus x bar 2 plus or minus my t star times the square root of s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. Okay, so plugging things in, I get 12.3 minus 7.6 minus my t star, which was 1.833, times the square root of 3.5 squared over 10 plus 3.4 squared over 12. So follow those calculations and see what you get. Maybe pause here to make sure you get the same calculations. What I got is a lower bound of 1.99 and an upper bound of 7.4. Okay, so 1.99 That's 7.41. All right, so in conclusion, we are 90% confident that the interval from 1.99 to 7.41 captures the true mean difference of average number of accidents per month in Department A and Department B. And if we interpret the confidence level, that means if we take many, many samples of size 10 and 12 and calculate a confidence interval based on each sample mean, about 90% of the resulting intervals should capture the true mean difference, or the true difference of means, sorry. Okay, so there we did it. That's a confidence interval for the difference of means.